Yeah, so this talk will be in two parts. Where we'll be giving an overview of research activities in the mathematics group as a whole. We have left out the monsoon group. They have two talks of their own and they have a poster. So then we took the entire slot for ourselves. And so Anish will be talking about the research in the probability group, and I'll be giving an overview of the geometry group. So, right, the first part is geometry group activities. So even amongst geometers, we have two well-defined groups, one working on minimal and maximal surfaces, and the second one broadly working on gauge theories, the geometric quantization of the moduli spaces that come from these gauge theories and some associated geometries. So in the minimal and maximal surface group is led by Rukmini Te. There are two external members in this group, Pradeep Kumar and Rahul Kumar Singh. We also have Rishabh Sharma, Mohammad Salim, and Tausaf Mani. And the gauge theory group consists of, again, Rukmini, myself, Saibal, Sumanto, and Kohinoor. So in case you have questions, you know to whom it should be directed. All right, so the focus of this group on minimal and maximal surfaces is on studying certain specific aspects of these minimal surfaces in Euclidean spaces, and maximal and time-like minimal surfaces in the Lorentzian 3 space. So just in one line, what exactly is a minimal surface and a maximal surface? So minimal surface is a surface that minimizes the area subject to a certain constraint. For example, if you say have a metal ring and you dip it in, say, a soap solution, you get a soap film out of it. Right? So that's one of your surfaces. The soap bubbles. Once you blow the soap bubbles, the area of the bubble, the reason you get a spherical shape is because that's the least area that you can get. Right? So that's the minimal surface in Euclidean 3 space. What are maximal surfaces? So once you shift from the Euclidean space to the Lorentzian setting, and you look at the surfaces in the Lorentzian space, then if you restrict the metric to that space, it needs to be Riemannian. That's the first condition. In other words, it needs to be space-like. And if the mean curvature of that surface is 0, then you call it a maximal surface. So the group has successfully identified some connections with L functions and certain Ramanujan identities. And they have used the theory of minimal surfaces for getting relations between different L functions. The current interests of the group that they're focusing on is studying the possibility of foliation of subspaces of R3 by minimal surfaces, maximal surfaces, etc. And what are the consequences of such a foliation? And also, they're interested in the study of interpolation of two real analytic curves by a minimal surface when the curves are close enough. Moving on to the geometric quantization. So one of the geometric quantization, broadly speaking, is a mathematical attempt of deriving a quantum theory from a classical field theory. I'll come to the differential geometric specifics in a moment. So one of the aspects of the work done in this group is the geometric quantization of various moduli spaces coming from the gauge theoretic equation. So more often than not, these various gauge theoretic equations and their moduli spaces, they carry a symplectic structure, and in some very nice cases, they also carry a hyperkähler structure. And it would be quite interesting to study this quantization because in a sense, we hope that it gives a quantum theory of these particular gauge theories. There are also certain integrable systems which can be geometrically quantized using co-adjoint orbits. One of the latest work of this group involves studying the finite Toda system. And this particular system has a description as a co-adjoint orbit. Now we know from the work of Constant and Soriao that any coadjoint orbit carries a symplectic structure, and therefore using the symplectic structure it's possible to give a quantization of this TODA system. Currently, there is a new idea that we are exploring, that is the geometric quantization of certain hyperkähler manifolds. These hyperkähler manifolds, they carry a specific SU2 action that sort of rotates the hyperkähler structure. So in essence, one hyperkähler structure cannot be distinguished from another. In the absence of such an article, for each hyperkähler structure, you can construct a certain line bundle that gives you the geometric quantization. It's called the pre-quantum line bundle. However, in the presence of this SU2 rotating action, one has something much more interesting, which is one of the recent works by Hitchin. It's called a hyperholomorphic line bundle, which is holomorphic with respect to all possible complex structures on the hyperkähler manifold. So one of the questions that we are exploring here is whether this hyperholomorphic line bundle can be obtained via a Quillen construction formalism. Because so far what we have seen in many particular instances is that all of these quantum line bundles can be obtained via Quillen's construction. So it would be interesting to see what happens in this scenario. This is more or less my work, where I have been focused on working on generalization of these hyperquinton invariants. In short, the idea here is to substitute the spinor representation with a specific hyperkähler manifold that has this rotating SU2 action. So what we end up getting is a nonlinear sigma model. And what we have been able to show is that at least the abelian generalizations can be expressed purely as a second-order partial differential equation in terms of an almost Hermitian metric on the underlying manifold, away from some singular locus. This is a generalization of one of Donaldson's results, and is applicable to a much wider family. One of the consequences of having such an expression is that at least when the underlying manifold is a Kähler manifold, one can define what is called as a composition law. So from a degree L solution and a degree M solution, one may be able to produce a degree L plus M solution using this result. Also, in the Kahler case, in a joint work with Indranil Biswas, we showed that the existence condition for the solutions can be computed quite explicitly in a much more simpler manner than was previously known. In a second work, I have dealt with hypersymplectic manifolds, which can be thought of as a pseudo-Riemannian analog of the hyperkähler manifolds, but with a neutral signature. And hypersymplectic manifolds, they have recently come into limelight once again because they have been produced as moduli spaces to certain gauge theories in the pseudo-Riemannian setting. In my recent work, I have given a classification of such hypersymplectic manifolds. They have some additional symmetries which were sort of neglected in the previous works, but that came up in the recent ones. And what this classification does is it gives you various examples of hypersymplectic manifolds that can be produced via a hypersymplectic reduction technique. Normally, when you apply such techniques in the pseudo-Riemannian setup, what you end up getting is a smooth manifold, but the hypersymplectic structure that descends is not smooth. It is always degenerate. But in this particular class, one never ends up getting such degeneracies. You'll always end up getting a smooth hypersymplectic manifold. So it just expands this entire known class of examples. Our current research interest, of course, is in composition law, as I mentioned. What I want to advertise in particular is this last part, which is of recent interest to myself and Anish. It's called the topological data analysis. What we are doing here is using topological methods to analyze data. This notion has been around for a while, but it is only now that people have been using it to its full strength. Mainly, the applications have been seen in biology, where, for instance, people have identified that there are not 2, but 3 types of diabetes. They could see that through topological analysis of the data that they had. Also, this was successful in identifying certain subtypes of breast cancer, and in fact, they identified a certain subtype for which the patient has a 100% chance of recovery. So using such methods have proved to be quite a powerful idea, at least in biology as far as we are seeing. So what we propose to the monsoon group is that why not try such an idea to analyze the monsoon data. But this, as you know, is not like a very well-defined question at the moment. We are yet to narrow down to the right question to ask and work with the data and look at its topology. So what we hope to gain from such a thing is what Ganga mentioned a while back. We hope to uncover some patterns from the monsoon data and see what we get out of it. So that's all from me. I'll hand this over to Anish.
Okay. I will be talking about most of the research projects done under probability group. There is basically 2 distinct parts, 2 distinct type of work that the probability group mostly focuses on. First part is mostly related to statistical mechanics. The problems they handle is try to show some kind of asymptotic results over the partition function, and in particular try to show tightness bounds over the log partition functions for Ising model and similar kind of problems. In general, if you actually just look at the 3 graph case, it's possible to come up with some very good results, but if you go slightly beyond 3s, this kind of results becomes much more difficult. And there are some other kind of problems also. For example, there is totally asymmetric simple exclusion process. This is a completely different kind of statistical problem than the Ising model kind of problems. Here, people try to study the fluctuations both in time and space, and at least for this scenario, this problem is highly related to the KPG equations. There are other kind of problems which, for example, sand pile models, where people try to talk about phase transitions and such things. The other class of problems that people deal with here are mostly in random matrix theory. These problems, at least for the random matrix case, people mostly target on the singular values and the asymptotic spectrums. One of the conjectures that was there early by von Neumann, this conjecture was there, is that for certain type of random matrices, the condition number goes in the order of size. Now, condition number is useful in numerical analysis because condition number tells us how good we can solve a problem. That is, if we are trying to solve Ax equal to b and trying to determine the x given by b, then how much accurate we can get based on the properties of A alone. It has nothing to do with the algorithm based on which we are doing the solving. There are other kind of problems also. For conditions number, we mostly need only the lowest and highest singular values. But in principle, one can ask similar question for next lowest, next highest, and these kind of problems are there. You can ask for k number of singular values, how they behave. And these kind of problems are normally handled in the random matrix community. Now there is another class of problems which is very similar to this conjecture. This is asking, suppose someone has given me an n cross n matrix with whose entries are either 0 or 1. Now here we can assume that is sparsely populated, that is only very few entries are 1. Now this kind of matrices normally represent graphs, right? So one can ask, when does these matrices are invertible? Now, in general, this question cannot be answered for a single matrix, but since we are talking in terms of random matrices, there are certain conditions based on the sparsity statements. It is known that the sparsity behaves like log n by n, but improving such a result is very important. So yeah, so these kind of problems are normally dealt under random matrix theory. I, on the other hand, work on random operators. Most of the results that I talk about are only valid in infinite dimension. My targets are mostly related to the regularity of density of states, and recently with some other people I have worked with the density about the derivatives of density of state, and shown that in the localized regime, the density of state is as smooth as your densities. On the other hand, I also work with multiplicity of the spectrum and other such things. As a special example, let me tell you something that is not normally seen by most of the people. This is a simple Anderson model over a graph, in this case inverted tree. If we take our random variables to be Bernoulli, then you can show that all the operator only has eigenvalues. What is more interesting is that this operator has infinitely many eigenvalues, which has infinite multiplicity. Now this property never holds if I take any kind of finite cutoff. This is one of the interesting things that can easily be seen for infinite dimensional random operators, but not for finite dimension. So yeah, so for random operators, these are the kind of problems that we deal with. And thank you.
Just take a single question.
Yeah.
So this is actually for Varun. Yeah, when you said about these hypersymplectic manifolds, so they also have an SU2 worth of of symplectic structures. Is that?
This is actually the SU11.
Oh, SU1.
It has an SU11 rotating action. So you have a two-sheeted hyperbola. So one part of this hyperboloid will give you the complex structure. The other two will give you the SU1.
I see. And is there a classification? I mean, you said you have classified some set of these manifolds with some symmetry, but in general, like hyperkähler manifolds exist only in 4n dimensions. Is there a similar this thing here also? It's also multiples of 4? Or?
Yeah, it's also multiples of 4. Yes, you're right. Yeah, there'll always be one.
4. And can you say anything more broadly general fact about these hypersymplectic manifolds?
One of the most odd things about these. Hello? Yeah.
Hi.
Yeah. So one of the most odd things about these hypersymplectic manifolds is it comes from two factors. So the first one is the indefinite metric. And that is the root cause of most of the problems that we see. For instance, I said, in general, when you look at the reduction procedure, in the usual case, even when you perform the reduction procedure with a compactly group, you end up getting a smooth hyperkähler structure. That is no more the case here. So, for instance, if you perform a reduction, say with U1 of a hypersymplectic manifolds, there could be points in the quotient space where you see that not the quotient space, but rather, okay, where these fundamental vector fields are 0. So, right, so in the quotient, this will be the singular locus where your hypersymplectic structure will fail. So these sort of phenomenon does take place. And the second thing is these hypersymplectic manifolds are always going to be non-compact. As long as they have this rotating action, they're always going to be non-compact. But there is also one other thing. Under some slightly restrictive conditions, one can produce what are called as the Paraquat anionic Kahler manifolds. So this hypersymplectic manifold, it actually fibers over a Paraquat anionic Kahler manifold. This is a picture that is reflected from the hyperkähler case as well. But here things are much more restrictive. You may get a structure of this hypersymplectic manifold as a say a metric cone over some Parasasakian manifold, but that may not necessarily, this Parasasakian may not necessarily come from some Paraquat anionic Kahler manifold. And this is in stark contrast with the hyperkähler case. In the hyperkähler case, it will always come. It will always occur as a total space of the frame bundle, coming from the frame bundle of a quaternionic Kahler manifold. So there are some of these differences that we are exploring at the moment.
Let us thank Varun and Anish once again.